The first thing that we're going to talk about in this question is the difference between verify and prove. With prove, you keep theta in there, and that's where you want your left side to equal your right side. Proving, when you've proven something, it means that it works for all angles. When you verify something, you're just checking one specific angle to see if it works for 30 degrees. But it doesn't tell you that it works for any other degrees. But verification, the process or the way that we're going to write a verification question is identical to a proof. It's more work, I think, than a proof. And in the end, you've only shown it works for one thing, but if you do the proof, you show it works for all of them. So the verification part is actually a little bit annoying because it only shows one value works, whereas the proving part shows that all values work. So for a verification, so in part A, if we were going to verify for theta equals 30 degrees, you still set up your left side, draw a line, set up your right side. You still want your left side to equal your right side, but instead of proving, you're going to plug in the value. So you have secant of 30 degrees, 1 plus cos of 30 degrees. That is on your left side. And on your right side, you have 1 plus secant of 30 degrees. So this becomes a unit circle kind of question. What is cos of 30 degrees? Right? That is root 3 over 2, right? So what is secant of 30 degrees? The reciprocal, 2 over root 3. And same thing over here. On the right side, we'd have 1 plus 2 over root 3. The main thing with verifying, the same thing that is a main thing with proving, is when you have two different things like this and you want to show that they're equal, the best strategy is to write both sides as a single fraction. So how do I work on the left side? Well, I could distribute this to get rid of brackets. That will give me 2 over root 3 plus, and 2 times root 3 and that'll be 2 root 3 on top and 2 root 3 on the bottom. Okay? At this point, you might even say, hey, that's equal to 1, and notice that they're the same. We didn't even get to the point where we wrote them both as a single fraction, but since they are the same, we can say left side equals the right side and have all of our fancy stuff at the end to say that we're done. So that's verification. Now, for proving this one, I asked you guys to prove it first, and you came up with a number of great proofs. So here's one of them. What this person did is they changed all of the secants to 1 over cos. They then distributed. Can you see that they distributed the 1 over cos into here? In fact, actually, what it looks like what they did instead of distributing is they made this a fraction over 1, and they multiplied the top by 1 and the bottom by cos to get this fraction. Okay? Now this is a single fraction, and what is the most typical thing that would happen after this is someone would work on this side to make this a single fraction. But what this person decided to do was to unsingle fraction it. Is that a verb? It's a very long verb. Unsingle fraction. They broke this up. If you're 1 plus cos theta all divided by cos, can you see that the 1 gets divided by cos and the cos could get divided by cos? And then they end with 1 over cos plus 1, which is the same as what they have over there. So we've got a proof. Another example. Okay? I like this example because it's done right here and they're perfectly fine, and then they make a little mistake going further, but it's such a common mistake I want you guys to see it because you're going to do it and you're going to do it often. So again, they change the secant to 1 over cos. But this person decided, I'm going to make both sides a single fraction. So they have the 1 plus cos over cos on this side. On this side, they changed the 1 over 1 to cos over cos to get a common denominator, and they got a single fraction. And like I said, at this point, they're the same. But you are going to be tempted to cancel when you're not allowed. So remember, with fractions, if you would like to cancel a factor, the factors have to be identical. But anytime there's a plus sign with something, that means this gets grouped together. And the only way you could cancel that grouping is if there was another 1 plus cos on the bottom. We are not allowed to cancel the cos within there. Okay? For example, look at it this way. 6 plus 3 divided by 3. Is that equal to 7? Can I just cancel these out and say that's 1 and 6 plus 1 is 7? No. Right? There's an order of operations that you know. When you see the numbers, you're like, no, I know my order of operations. I have to do the 6 plus 3 first. And then I can divide by 3. So I'm not allowed to cancel these values. And so it's not equal to 7. If you were like getting all nervous, it's 9 divided by 3 is 3. That's the actual answer. But it's going to be so tempting to cancel things out like this. The main thing is whenever you're adding or subtracting things, they get grouped together. And only when you're multiplying a set of things and you have an identical thing on the top of your fraction with an identical thing on the bottom of your fraction, then you can simplify. Okay. This one is, I'm sorry, it's a little bit light, but what I like about this one is instead of changing everything to cos, this person decided to change everything to secant. So it's showing you that there's different ways you can go about doing these things. A most common strategy is changing things to sine and cosine, but it doesn't necessarily mean you have to do that. So sometimes once you've proven one thing once, you might want to look at the same proof and see if you can come up with a different creative way to figure it out. And then see if you can figure out what's the shortest possible way you can make a proof. I actually think with this one, when they change the cos to 1 over secant, and then they distribute, secant times 1 is secant, secant times 1 over secant is 1, and you're done right away, and it's nice and short. And so it's a very nice proof, but it's sort of going opposite of what a common strategy is. Let's see, is that our last one of those? Yes. Okay, so part B, the verifying part. So again, I'm going to split left side and right side. I'm going to plug in 30 degrees. On your pie plate, what is tan of 30 degrees? Square root of 3 over 3. And so cotangent of 30 degrees will be 3 over root 3. Whew. Both of these sides do not look similar at this moment. Okay? So what are we going to do? We're going to try and use our strategies to get a single fraction on both sides. I'm going to get a single fraction on this side. This one looks easier. Start there. Get a common denominator. We're going to get 3 minus root 3 all over 3. On the right-hand side, we have a single fraction on the bottom. Can you see that we don't have a single fraction on the top? So when we're trying to overall make a single fraction, we will start by multiplying by root 3 over 3. And that will give me 3 minus root 3 all over root 3 on the top. Big thick line for my middle line over 3 over root 3. Now I have a single fraction on the top, a single fraction on the bottom. Now I can multiply by the reciprocal. Notice how much space I'm leaving in between here so that I can really see what I'm working with. Whoops. Yeah, that's right. What did I do wrong? 3 over root 3? No. when I multiply by the reciprocal there. Oh, I missed the denominator. I knew something looked a little bit strange because it was going to simplify nicely for me, and it wasn't all of a sudden. So now, this is grouped together. Okay? These ones are multiplied here. Do we have any factors that are identical? Yes. We would be allowed to simplify here because we're multiplying and they're identical. We would not be able to simplify that root 3 out because it gets grouped together with the other 3 with the minus sign. And then after those are simplified, we have 3 minus root 3 over 3, which is the same and we're done. Now for the proof of this one, I had hoped you guys would come up with these proofs, and you did a wonderful job of coming up with a multiple different ways to do the same proof. Which one do I want to start with? No. Yes. Okay. So, if you're stuck, the most common strategy is to say, let's change things to sine and cos, because every single function can be reduced to sine or cos, and work with that. That strategy will work. It will not always be the fastest strategy, but in this case, you can change the tan to sine over cos. You can change cotangent to cos over sine. And in this case, this example also uses, I want to get both sides to a single fraction. And earlier I said, if you can change things to sine and cos and get both sides to a single fraction, where we're currently at, you'll be able to solve all of the questions. We will get some later on that have some added difficulty to that, where that won't work completely, but you will still get 2 out of 3 or 3 out of 4 on that question because it's a great strategy. So what have we done? We got a common denominator, wrote this side as a single fraction, cos theta minus sine theta over cos theta. Got a common denominator, made a fraction on the top, fraction on the bottom, multiplied by the reciprocal. Here, this would get grouped together, but the signs cancel out because they're identical factors, and we have the same thing on both sides. So I wanted to start with that one because that's our common strategy, changing to sine and cos. But in this one works really well. Another strategy to think about is if you look at both sides. One side's tangent, one side's cotangent. Another really good strategy is to say to yourself, well, if I can get everything with one thing, if everything was tangent, then there's probably a good chance I can make them equal. Or if everything's cotangent, there's probably a good chance that everything will equal. So this second example, this person changed everything on the right, all the cotangents, to tangents. Okay? Now, you had a piece of scrap paper that you probably were running out of room. On your exam, each of these steps should be written underneath each other so that you can see the flow of where it's going. But for this one, we're going to say this person went from here, then went to here, to here, to here. They went woo, right back to there, and then like that. Okay? So what did they do? They changed it to tangent. They said, I want to get a single fraction on the right-hand side. So I got a single fraction on the top, a single fraction on the bottom. That allows me to multiply by the reciprocal. They multiplied out on the reciprocal here and then factored to simplify it. Can you see that if they wanted to, they could have simplified here and got to this a lot quicker? But that's not wrong to multiply it out and then factor and solve after. But we could have gone one. If you can see to simplify early, it does make your life easier because you can get to a point a lot quicker. And then, boom, we've got left side equals right side, and we're done, which was probably written right here. And I just cut it off. And finally, we had one person decide, I want to change everything to cotangent. And this is the probably the shortest proof on this one. So if I change the tangent to 1 over cotangent, then I need a common denominator. And I put it as a single fraction. Boom. 3 steps, done. So there are multiple different pathways on any proof to start to finish to get it right. There's the common method, right? Changing to sine and cos. This one had a little bit, it's not that bad. And if you like that common method and you get really good at it, it can be the quickest one for you, right? But if you want to start getting creative and thinking of different ways, you can say, maybe if I change both sides to the same function, that will work for me. So here, let's change both sides to cotangent. Or we can change both sides to tangent. And then we can get our questions to work that way as well. Okay, so 3, 5, 6, and 7 II are your questions. You'll notice in 7, the reason I chose II, I think 7I is verify. So I just that's kind of annoying. Hopefully you could do it with numbers, but I'm going to get you to practice proving more.